So, if you have seen Cook-Levin's theorem, okay, to show that SAT is NP hard. So, this is essentially along the same lines as Cook-Levin's theorem. Okay. So, essentially we take a Turing machine which has a certain running time. So, now this has deterministic running time. So, L is decided by Turing machine which has deterministic running time T of n, and I will look at the different configurations of this Turing machine for different levels, and I will try to build a circuit by looking at this matrix of configurations. Okay. So, essentially that is the idea. So, I will just quickly go over the proof because yeah, I mean if you have seen it then you can, it is good to have revisit it again, but otherwise I will skip maybe some details and that can easily be filled up. Okay. So, let us look at a sketch of the proof. Okay, start here. Let L be decided by a Turing machine M equal to Q sigma delta Q naught F having running time T of n. So, Q is the number of states, this is the alphabet size, this is the transition function, start state and the number of accept state, and we will assume again without loss of generality that the Turing machine has a single tape. Okay. So, it has a single tape. Initially we only have the input x written on the tape, everything else is blank. What else do we need to assume? Yeah, I think that is good enough for us. Okay. So, now so what is the transition function of the Turing machine looks like? So, the transition function of a deterministic Turing machine can be thought of as a function from Q cross sigma to Q cross sigma cross L comma R. So, essentially what this is saying is that at every time instant when I apply delta, the Turing machine looks at the current state. So, basically there is a head in the tape. Okay. So, it looks at the current state, it looks at the input being pointed to by the head, and then it moves to some other state, it replaces that character with some other character and the head moves either left or right. Okay. So, that is what we will assume delta does for us. So, now it is easy to see that delta is actually independent of the input. Okay. So, delta is basically a constant sized function because all these are bounded sets Q sigma. So, both of them are sets of bounded size. So, the first observation is that delta can be represented by a constant sized circuit, and when I say constant I mean that it is independent of the input. So, essentially it is a circuit which looks like this. Okay. So, let us give it a name, let us call it as C delta. So, C delta takes as input some Q in Q and let us say some A in sigma, and then it outputs some, well not some, but the Q prime corresponding to whatever delta is. So, it outputs a Q prime in Q, it outputs A prime in sigma, and it let us say outputs whether to go, it outputs a bit which says whether you have to go left or right on this. Okay. And just for the sake of uh, I mean ease of implementation, you can assume now that the circuit that we will be building has alphabet which are elements from capital Q, sigma, L, R, okay, all these. So, this is anyway a bounded set. So, but you can assume the alphabet to be over this, and then finally you can just replace all of this with strings over 0, 1. It does not matter, I mean it is the same thing. Okay. So, now what do we do? Okay. So, consider a Tn cross Tn matrix, say let me not use M, I have already used M over here, let us say P, okay. Where the ith row of P represents the configuration of M at ith time step. Okay. So, now what is a configuration? So, a configuration of a machine consists of 3 things. Okay. So, a configuration consists of firstly the current state, secondly the tape contents, and thirdly the position of tape head. Okay. So, we will see a method to encode all these 3 things into the Turing machine. Okay. So, now note that, so the longest, so of course, the state is a constant thing, but the tape content, so at any point in time the number of cells used in this machine M can never exceed T of n, because that is the total running time. You cannot write beyond T of n, T of nth cell, you cannot go that far, because at every step you can only move by one step. And the number of rows is of course the running time, because the running time is bounded by T of n, therefore the number of rows is bounded by T of n, and the number of columns is also bounded by T of n. Now, let me be a little bit more specific about the contents of the rows, sorry, the contents of the entries. So, P of I comma j will store the following. So, firstly it will store the letter in cell J at I will write this later on, the letter in cell J. Secondly, it because Okay, just let me complete this, then it will be easier. I mean, I am just describing what the matrix is. Let me complete the description, it will be easier then. Let me just change this a little bit. So, the first one will be the whether the head points to cell J so this I can call as, what do I have it as, head present bit. So this is a single bit which stores this. Second is the letter in cell J, and the third is the current state. Okay. So, these two together will be the data part, and this is the head present bit. Okay. And all the above are for time step I. Okay. Okay. So, now coming back to your question, why is the number of columns bounded by Tn? Okay, because see, what are we storing in this matrix? So, in this matrix essentially we are storing the information about cell J. Okay. So, whether the head is pointing to cell J or not at any time I, what is the letter in cell J again at any time stamp I, and what is the current state when it is at when the head is pointing over here. If we, I mean, if the head is not pointing, the current state does not matter, but anyway we can keep something. What is the current state? Okay. Now, the point is that if the machine has a running time Tn, okay, then at no point in time can basically it go beyond Tn many cells. Okay, at no point during its computation, because at each step it can only move one bit. So, even if we assume that at each step it moves left, it moves right, it can only go up to Tnth cell. So, we do not have to store anything beyond, we do not have to store any information of any cell beyond T of n. And once we have stored this, note that this actually represents a configuration, because I have the current state. By looking at the entire row, I know the tape contents, okay, that is from this second point, and the position of the tape head is obtained by again looking at the entire row and seeing for which J is the head present bit set. Okay. So, now we will see how we design a circuit. Okay. So, the next step is note that any entry of Pij, what does it depend on? What does an entry of this matrix depend on? Huh? Pi minus 1, that is the previous row, and so in terms of the matrix, so Pij will depend on which cells of the matrix? So, if I kind of draw a picture, right, let us say that I have, so this is my ith row, let me just let me draw it over here. Okay, and this is, let us say, my jth. Okay, so this is my Pij. What does it depend on? So, I have the I minus 1th row over here. So, of course, it will depend on the previous cell. Okay, I mean, I am sorry, I j minus 1, this one, how? No, so if I have to decide that what will be the, I mean, what will be the contents of this cell. Okay, so the for the contents of this cell, I have to set three things: the current head position, the current letter, and the current state. Okay, what does it depend on? Yes, but suppose let us say the head is pointing to some position over here, this cell. Which cell? This one. No, see, if it is actually something which is, let us say, beyond I j minus 1 or after j plus 1, then it cannot affect this, and whatever was here, the same thing gets copied over here. Okay, so the state, only the neighboring cells will decide whether the value changes or not, whether that character changes or not. Okay. So basically it will depend on just these three cells, okay, that is j minus 1th cell, jth cell, and j plus 1th cell. Okay. So Pij depends on, or depends only on P I minus 1 comma j minus 1, P I minus 1 comma j, and P I minus 1 comma j plus 1, only these three cells. Okay. And exactly how it depends on, what is the dependence, we can characterize that as well. How do I write this? Okay. So we build a constant sized circuit, let us call it Cij, as follows. So, if the head present bit of P I minus 1 comma j is set, then look up the circuit C delta. to find the data part of Pij. Okay. So, suppose if for this cell the head present bit was set, okay, that means it was set to 1, okay, it means that the head was pointing over here. Then I just look up the function C delta, that is whatever was the current state in Pi minus 1j, and whatever was the current letter in Pi minus 1j, I just feed it to C delta and I get what Q prime and A prime I get, and I just put it over here. Okay. So, that is the data part. Now, what about the left right part? Okay. So, I mean what about the head present bit? Huh? I am sorry? No, I am talking only about the data part of Pij. So, if the head present bit of this is set, then this is how I compute the data part of Pij. But what about the head present bit of Pij? Say it again.
So, if the C delta gives me left,
C delta on what? Of what?
on the whatever the Pi minus 1j contents are, if on that content the C delta outputs left, then the Pij content remains intact.
No. No. So, if the head present bit of this is set, okay, which means that, huh?
Pi minus 1j, okay.
No, not j minus 1, Pi minus 1j. So, if let us say the head is pointing over here, it means that I have to apply the Turing machine, I have to apply the transition function on the data part of this cell, right. So, I look at this, the state over here, the letter over here, I apply it and I get Q prime and A prime for Pij, okay. That is it, I do not look at whether it is going left or right immediately. Now, I have to set the head present over here. Now, how is the head present bit set over here? So, the head can come to this position either from here or from here, right. Huh? From Pi minus 1j, from Pi minus 1j it will go to either here or here, but it will not come here, okay, but I do not care about that, I just ignore about that. When I go to these two cells, then I will figure it out. So, now the remaining point is, now if the head present bit of Pi minus 1, j minus 1, if the head present bit of this or Pi minus 1 j plus 1 is set, then look up C delta to find if the head comes to the ith cell. Okay. Now, the head can come to the ith cell only from either I minus 1 or I plus 1. So, if the head position bit of either these two entries were set, you look up both those entries. Okay. So, look up Pi minus 1 j minus 1, apply again C delta on the contents of this and see, now you check whether it is going left or right. So, from this if it is going right or from this if it is going left, then you know that the head present bit of Pij has to be set to true, otherwise not. That is it. So, this allows us to compute Pij for each and every ij. And the reason why this is a constant sized circuit is because I am looking at only 3 cells, okay. Each of these 3 cells have constant amount of information and I am able to compute it, okay. So, now what remains? So, here what we are doing is kind of an iterative step, right. So, to get Pij I am looking at Pi minus 1, but how do I get the contents of the first row? There is no 0th row, right. So, the contents of the first row will be basically dependent on the input, okay. So, for the first row of P, the first n cells contain the input x and the current state of P11 is Q0 and the head present bit of again P1 comma 1 is set, everything else is set to false. This is set to true. When I say set, I mean set to true, everything else is set to false. This we are doing because we assume that at the beginning, as I said, we assume that the head position is at the first cell and the tape contains the input x. That is exactly what we are characterizing. This we can actually look up the input. So, we know what, so given any x we can actually design this, and now subsequently for every I greater than or equal to 2 we can build for Pij. And when do we accept? When do we accept? When we reach some accept state, right. So, how do we know we have reached an accept state? So, basically we can take an OR of the following. So, for, well, yeah, so the definition of acceptance of a Turing machine is whenever it reaches an accept state we accept the input, we do not care what happens after that. So, basically we can take an OR of all the cells whose head present bit is set, okay. Well, actually there are, okay, so let me do it in a different way. So, let us do it in the following way. So, look at the Pnth row, okay. So, if the cell whose head present bit is set contains an accept state, then yeah, I mean it is okay, then accept. And one other thing that we need to mention over here, because we are looking at the Tnth row, is the following, that assume without loss of generality that once M enters an accept state, it stays there forever. You can modify the transition function to make sure that from an accept state it does not go to any other state. So, therefore, we know that if it had entered an accept state at any row, it will remain at an accept state in the last row as well. Okay. So, this is I mean more or less the entire proof. So, what have we got as a result? That if I take a Turing machine which runs in poly time, then it can be simulated by, let us say if it runs in n to the power k time, it can be simulated by circuits of size n to the power 2k, which is again polynomial. Okay. So, P is in P slash poly. In this circuit, we are computing all the contents at each step, yes. The entire matrix we are computing. Okay. So, now actually this computation can be made more efficient. So, instead of taking T n square, there is a result by Schnorr and Pippinger who showed that you can actually simulate in time in size T n log T n. Okay. And that kind of uses the fact that you do not have to look at the end, you do not have to store this entire thing, okay, because from 1 you only go to these 3 neighboring things. So, you can actually make you can make the Turing machine into an oblivious Turing machine. So, an oblivious Turing machine is a Turing machine whose head position does not depend on the input. Okay. So, for every input of a fixed length, the head position is the same at any time step j. So, you can actually make the Turing machine into an oblivious Turing machine, and then you can show that for an oblivious Turing machine, this can be done by a linear size circuit. And to make a Turing machine into an oblivious Turing machine, there is a blow up of log n. So, that is a more that is a better upper bound, and that is the best that is known. Okay. Okay. So, when you say P slash poly uniform, what do you mean? So, you mean let us say what kind of uniform, log space uniform or P. So, if you say P uniform, what does that mean? That means that there is a polynomial time machine which given n can generate the circuit, and now then it will become equal to P, because then what you can do is that you can generate the circuit, and on any input you can actually kind of do a traversal of this circuit in P, and you can find out whether it is accepting the input or rejecting the input. So, that is the other side, but that is possible again. So, traversing a circuit, so given a circuit and an input, so this is called the circuit evaluation problem. In fact, again this is an interesting result, that this circuit evaluation problem, so the circuit evaluation problem is you are given some circuit C and you are given an input X, and the question is, does C accept X? So, this problem is not just in P, it is actually P complete as well, it is hard for P as well. Okay, so, entire P reduces to this. So, by this result it shows that if you take any notion of uniformity for P slash poly, then it is equal to P. Okay. So, any other questions?